we're going to look at the graphs of exponential functions a little bit more closely than we have in the past. We know the general look of an exponential function, but do we actually know the key points? I defined exponential function as being b to the x power. X is the exponent, so the variable is in the exponent. That's what makes this an exponential function. I left you this little note here. Any number that is raised to the 0 power will always equal 1. 2 to the 0 power has to equal 1. A fraction like 1/3 to the 0 power has to equal 1. So that is going to create one of our key points for all of these graphs. So I'm going to create a table of values here. And okay, so for 2 to the x, let's create a table of values. So let's look at the values -2, -1, 0, 1, and 2. I'm going to start with the one I know. Anything to the 0 power is 1. So 2 raised to the 0 power is 1. How about 2 raised to the first power? 2 raised to the first power is 2. How about 2 squared? 2 squared is 4. Here's something you may not know. Going backwards, something called the negative exponent rule. Anything to the negative exponent will actually turn it into a fraction. It's the reciprocal of the number. So 2 to the negative first power would become the fraction 1/2. 2 to the negative second power would become the fraction 1/4. So what does the graph look like when we plot those points? There's my y-intercept at 0, 1, 1, 2, 2, 4, 1/2, 1/4. So it's an exponential increasing or exponential growth graph. It has something else that's kind of a key feature. It has this dotted line at y equals 0 called an asymptote. And we haven't talked about an asymptote very much. An asymptote is a line that a graph will approach. So see how it's getting closer and closer and closer to 0? Could a fraction ever actually equal 0? So it's going to get smaller and smaller and smaller. So it's going to go 1/4, 1/8, 1/16, 1/32, 1/64. It's going to get smaller and smaller, but it's never going to actually disappear and go to 0. So how is the graph of 3 to the x any different? Let's do the same key points. Let's start with the 0 power. 3 to the 0 power is 1. 3 to the first is 3, and 3 squared is 9. Going backwards, we would have the points 1/3 and 1/9. So I start at 0, 1, 1, 3, 2, 9, 1/3 and 1/9. So it looks very similar to the graph that I just drew, slightly steeper, isn't it? It also has an asymptote at y equals 0. These are both exponential growth functions. So as I read my graph from left to right, the graph is going upwards. All right, let's look at two exponential decay or decreasing functions. 1/2 to the x and 1/3 to the x. They're directly related to the graph above it, as we will see with this table of values. So we still want to do -1, 0, 1, and 2. So I'm going to start back at 0 again. Anything to the 0 power is 1. What about the 1/2 and I raise it to the first power? 1/2 to the first power would still be itself, 1/2. What about if I square it? If I square 1/2, 1/2 times 1/2, I would get 1/4. What if I take 1/2 and raise it to the negative first power? Now I'd be at 2. Raise it to the negative second power, now I'd be at 4. This table is directly opposite the table that we just did for 2 to the x. These are just reflections over the y-axis. So when I graph these points, I will get a reflection over the y-axis. Same steepness, same asymptote, just one is increasing and one is decreasing. And the same is true of 3 to the x and 1/3 to the x. When I create that table of values, anything to the 0 power would be 1. 1/3 to the first is 1/3. 1/3 squared is 1/9. Raise it to the negative first power and you'd be at 3. Raise it to the negative second power and you'd be at 9. So when I plot those points, it's going to be a reflection over the y-axis. Lastly, I should write down that it has an asymptote at y equals 0. Okay, let's summarize kind of the important facts about these exponential graphs. I used 2 to the x and 1/2 to the x, but these facts apply to 3 to the x and 4 to the x and 5 to the x, any base bigger than 1, any base that's a fraction. The domain for both is always going to be all real numbers. I can plug any value I want. I can plug in negative values, decimals, 0, anything I want for x. The range, however, will always be greater than 0 because I never touch that asymptote at y equals 0. So I'm going to write y equals 0 is the horizontal asymptote. We know that the y-intercept for both graphs was at 0, 1. Growth is increasing while decay is decreasing. Discrete means, is it a dotted graph or can I connect the dots to make it continuous? So it's a continuous graph and it looks like this. Draw a rough sketch. This one would also be continuous. It says, do any of these facts change if we change the base to something different? Nope. Right? All of these are going to follow the growth. All of these are going to follow the decay. So there's really just one set of rules for exponential functions, kind of like quadratics, right? They always have the parent graph that we know and love, 0, 0, 1, 1, 2, 4, and 3, 9. All right, so now let's take a look at the transformation rules that we should know from quadratics. To me, this is one of the key learning points for Algebra 2, using all these transformation rules on a lot of different functions. Here's my example, 2 to the x. How do I write that with a vertical shift up? Something like 2 to the x plus 9 would shift it up 9 units. What if I want to do a vertical shift down? I would do 2 to the x minus 9. So up is plus 9, down minus 9. Now what if I want to go left and right? Inside the parentheses on an exponential function actually means you're up in the exponent. So if I want to go to the right, I would write 2 to the x minus 5 up in the exponent, and that would go right 5. Or 2 to the x plus 5 in the exponent would go left 5. And these could all be, these could all be either y equals or f of x equals. If I want to reflect it over the x-axis, that is upside down. You put a negative in front of the whole function. If you want to flip it over the y-axis, you put it with the x value. And remember, that changes it to the fraction 1/2 to the x. So it makes sense. Remember, increasing turns into decreasing, a decay graph using that negative exponent. A vertical stretch and shrink. So I could actually increase the steepness of my graph by multiplying out front here by a different number. And I could decrease the steepness of my graph by using a fraction. So there's a stretch or a shrink, and we're going to look more at this part next time, but we're going to look at these transformation rules a little bit more today. So I'm going to complete these 4 graphs with you so we can practice graphing them by hand. And then to finish up today's lesson, you're going to complete this graph match on the back using transformation rules and submit this guided practice for today's work. But first, let's practice with these graphs. So it says use the graph of 2 to the x to sketch the following transformations. So my recommendation is on all of these graphs, we sketch the parent function. And we have the parent function on the other page. It was 0, 1, 1, 2, 2, 4, 3, 9, 1/2, 1/4. So what is this doing to my graph? It's a plus sign with the x, so that's going to shift it left 3. So I'm going to take each of my points, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, right? So here's my new graph that's been shifted to the left 3 units. Where's that asymptote? It's still at y equals 0. All right, let's put that parent function on here again. 0, 1, 1, 2, 2, 4. Oops, did I say 3, 9 over here? That's my bad. 2 cubed is only 8. This should have been 2, 8, or 3, 8. 2 cubed is 8. So this should be over 1, 2, 3, 8. 1, 2, 3, 4, 5, 6, 7, 8. Always a good idea to do your graphs in pencil. I broke my own rule. Here's 2 to the x. What does this plus 3 do? It shifts the whole graph up 3. So that means it also shifts the asymptote up 3. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So that means the asymptote is going to go at y equals 3. All right. What reflection is this? Do you remember? And then I've got a different one over here. So this reflection is actually going to be over the x-axis, so it's going to be flipped upside down. So if we have the key points of the parent function, it'll be easier to reflect it over the x-axis. So the asymptote is not going to change. It's still going to be at y equals 0. So I'm going to flip this point upside down, this point upside down, this point upside down, 1, 2, 3, 4, and then 5, 6, 7, 8. And then these are just like fractions. All right, so whoa, here is my graph that's been flipped over the x-axis. In my last function, I have a double transformation. So this is going to flip over the y-axis and shift everything down 4. So I'm actually going to move my 1, 2, 3, 4. My asymptote will move down to y equals -4. And if my original function went in this direction, I think I can do it in this direction, not without having to graph the original. So it would be 0, 1. I'm just pretending that now this is my x-axis. Over 1 up 2, over 2 up 4, 1, 2, 3, 4, 1/2, 1/4. So if you've moved your asymptote, you can just pretend in your mind that this is really the new x-axis, and then you can just base it off of that x-axis to save you a little bit of time. So now you're going to try just this graph match. Each of the graphs above matches to a graph below. I recommend figuring out which of the graphs at the bottom is the parent function first, and then figuring out all the different shifts. Try to do it just practicing the transformation rules, not plugging them all into a calculator, and make sure you post it in Google Classroom. Thanks.